Welcome to Study Loop.
This question says that the reaction of CO2 with solid carbon goes to 2CO and has a Kp, or an equilibrium constant with respect to pressure, of 5.78 at 1200 Kelvin. And it's two parts, and the first part asks us to calculate the total pressure at equilibrium when 4.45 grams of CO2 is introduced to a 10-liter container and heated to 1200 in the presence of 2 grams of graphite. So there's a lot of parts here, but let's break it down. It tells us the amount of starting material of each of the reactants, 4.45 grams of CO2 and 2 grams of carbon. From this, we can calculate the number of moles of each of our starting reagents to calculate which of the two reactants is the limiting reagent. And if you did this, your units are going to cancel out. Just divide by the molar mass of CO2 or just carbon, and you would get 0.1011 moles of CO2 and 0.1665 moles of carbon, solid carbon or graphite. So therefore, CO2 is clearly the limiting reagent in this, so we'll have more than enough graphite to make this reaction go. So this is what we're going to work with. But all of this is done in pressure because the equilibrium constant is done with respect to pressure. So we're going to have to convert moles to pressure. So if we use PV equals nRT, make this more clear, that's a V, we can solve for pressure. We have volume. It tells us in this question that it's 10 liters. Write that over here so we remember, 10 liters. We know the number of moles of gas. We have it here. We know the ideal gas constant, 0.08206 liter atmosphere per mole Kelvin. And we know the temperature, 1200 Kelvin. So if you plug in everything you know and get P by itself, you will find the pressure equals 0.9957 atmospheres. So that's our initial pressure given this amount of CO2. So I'm going to put that on this ice table under I for initial, 0.9957 atmospheres. Great. I'm going to cross out this entire section for graphite because graphite is a solid. Solids don't change concentration, so this is not going to be contributing to the equilibrium constant. And for CO, we don't have any at the beginning, so I'm going to put a 0. Change, we're going to lose some amount of CO2, and we're going to gain twice the amount of CO. Because of this 2 here, we'll gain 2 moles of CO for every 1 mole of CO2 we lose. So I can write the equilibrium amount in an equation, 0.9957 minus x and 2x. So the initial minus the change gives us the equilibrium constant, or the initial plus the change gives us the equilibrium concentration. So I can plug these two values into the equation for Kp. Kp equals the pressure with respect to carbon monoxide, or CO, squared, because I have this 2 here, divided by partial pressure with respect to CO2. Okay? And this is 5.78. This equals, the value we got for PCO is 2x, so this is 2x, and that whole thing is squared, divided by 0.9957 7 minus x. Okay, and I'm not going to work all this out. You just have to rearrange to get x, or really rearrange to get a quadratic equal to 0. Then you can just use a quadratic calculator to find x, and you will find that x equals 0.677. Great, so if you were to plug those two values back in here, I'll put this in parentheses, sorry, there's not a lot of space, there's a lot going on here. If you put 0.677 in for x here, you would find that you would have 0.3184 atmospheres of CO2, and you would find that you have 2 times 0.677, or 1.3546 atmospheres of carbon monoxide. Right, so in these parentheses here are the pressures at equilibrium of CO2 and CO. And so the answer for A is the total pressure at equilibrium. So we would just sum these two values together. So I'm going to write the pressure total equals, and if you sum those together, you would get about 1.68 atmospheres. So this is the answer for part A. This is the total pressure of both gases at equilibrium that we found based on the initial values or initial amounts of two of the reactants. Part B says, what if the presence of the graphite was only present at 0.5 grams, so not 2 grams, 0.5. We could redo this, 0.5 grams of carbon. I'm not going to write out the fraction, but this is equal to 0.0416 moles of carbon. Now you can see that this value is much less than the number of moles of CO2 we have at the beginning. Therefore, graphite is going to be the limiting reactant in this reaction, and we're going to use up all of it because there's a 1-to-1 ratio. For every mole of carbon we use, we'll use 1 mole of CO2, so we're clearly going to go through all of this before we get to CO2. So what we can do is to find the pressure at equilibrium. Our initial pressure stays the same, but the change is no longer going to be how we did it here. The change is going to be whatever this number of moles equates to in terms of pressure of CO2. So basically, if you subtract the number of moles here from the number of moles here, you'll get some final number of moles. That's 0.059 moles of CO2. You can convert that to atmospheres as we did previously. You would get that it's 0.58 atmospheres. So that's the equilibrium pressure of CO2 in part B. It's 0.58 atmospheres. You could then calculate the difference between 0.99 and 0.58 atmospheres. That'd be your change. You double that change to figure out what the change of CO would be given limiting amounts of graphite. So I'm sorry I can't write all this out because there's not a lot of space, but you'd have that change here, and you would find that the final pressure of CO, if you just plugged it back into here, you'd have 5.78, whatever that change is here, and then you'd solve for X, and you would find that the pressure of CO, or the total pressure now, but still given the pressure of CO, is about 1.41 atmospheres. So that's the total pressure if you had limiting amounts of carbon. Again, you're doing everything the same way. The only difference is the equilibrium you're going to calculate based on using all of the carbon in the reaction.